Okay, good afternoon, everyone. Welcome to this webinar as an introduction to helium ion microscopy hosted by MCFP. So we'll get started in a moment, but just before we do that, a little bit of housekeeping. So if everyone can keep their microphones muted and video disabled, just to keep it nice and clean and tidy. You can add questions into the chat as we go along, and we'll try to address as many of these as we can at the end, but bearing in mind that we probably won't be able to get through everything. But what we will do is take down all of these questions and we'll respond to all of them for you in a Q&A post via LinkedIn. So you'll be able to see all the questions that everyone has asked and our responses to all of those. And just to let everyone know, this webinar is being recorded. We're recording this to the cloud. So at the end of this, once it's been processed, we'll share a link to everyone. So this is particularly helpful for our international viewers that perhaps want to see this webinar as well. So you'll be able to view it again once that link is ready. So a little bit about myself. Many of you probably haven't met me before, or maybe we've interacted via email, but my name is Anders Barlow. I'm an academic specialist at the MCFP, the Materials Characterization and Fabrication Platform, where I look after the helium ion microscope, the electron microscope, and our Raman spectroscopy capability as well. MCFP is also a part of ANT Victoria. We are one of the hubs of the ANT Victoria node, and the helium ion microscope is an in-kind contribution to ANT as well. MCFP is quite a multidisciplinary platform. We spread across a number of areas in materials characterization. We have a number of different capabilities. And this is our team, with each of us managing a different node under the management of Lauren Hyde. And we cover a lot of different areas. So if there's anything here that piques your interest, or if you'd like to visit our website, please do so. Feel free to contact us and ask us any questions about how we can help with your research. So it occurred to me while I was putting this together that we do have some international viewers, and we've generated a lot of interest with this particular webinar. So I thought maybe it would be useful to quickly go over where all of the helium ion microscopes are around the world. And including the nanofabs and the Orion Plus, there's a bit over 100 of these microscopes around the world now. So if you are listening in from any of the countries where you can see a pin here, there is a microscope nearby to you. So you can visit this website and click on the pin and see whereabouts that microscope is located, and you can contact your local researchers there to find out about how this technology could possibly help you. We are, of course, talking to you from Australia, and we have microscopes in 3 locations in Australia: Brisbane, Sydney, and Melbourne. We actually have 4 microscopes in Australia. So there's 1 in Brisbane, 1 in Sydney, and 2 in Melbourne. So I'm talking to you from Melbourne, of course. This is the Melbourne CBD. And I'm talking from, or we come from, the University of Melbourne, which is just north of the CBD. And I've marked on the map here where the platform is, or where our platform locations are. So this is the Parkville campus of the University of Melbourne. And we have number 40 of the Orion nanofabs, and is located here in the Department of Biomedical Engineering. The rest of the platform capability is up in chemical engineering here, and much of this area is the Parkville University of Melbourne campus. So what do I want you to remember from this webinar? These are the key attributes that we consider to be very important about the helium ion microscope. So this is what I want you to remember about the microscope. It has high resolution and a high depth of field owing to the gas field ion source that we use. We can image insulators without a coating due to the use of an electron flood gun. And due to the ion surface interaction, we get good surface sensitivity, and we can do things like ion dosing and nanofabrication. So these are the attributes that we leverage all the time with our helium ion microscope. And this is really what I want you to take away from this webinar. This is what I view the helium ion microscope to be all about. And we're going to break this down as we go through this hour and go through where each of these attributes come from, and then go through some examples and some case studies of how our researchers are applying these different attributes to their research. So just a quick overview of the broad nature of what we do with our microscope. Much of what we do, of course, is imaging. And we're using the resolution of the microscope to image nanoscale and nanostructured surfaces. We also image insulating materials and soft matter materials like biological structures. And then we're using the beam to modify surfaces as well. So we're doing materials engineering by either dosing areas or punching small holes and engineering structures into materials, or we're doing micro and nanoscale fabrication, actually removing material to create devices. Okay, so let's go through how we're able to do that with this microscope. So let's start with the gas field ion source. It's based on the field ion microscope, which was developed in the 1950s, whereby the researchers took a very, very sharp tungsten tip, they cool it down to cryogenic temperatures, apply a high voltage, and then surround it with pure helium. And then beneath this very sharp tip, they had a phosphorescent screen and a camera. And what they would see coming from this tip is a projection of the atomic structure of that tungsten tip. So on the phosphor screen, they got all these little bright spots, and each one of these bright spots represents the emission from an atom on the end of that tungsten tip. So even though the tungsten tip was very sharp, it still had a spherical end form like this. Each one of these little protruding atoms at the very end creates, when under a high voltage, an ionization disk, which are represented by these blue crescents here. Each one of these ionization disks, when the helium approaches close to it, is ionized and then emits radially outwards from the tip. So you can imagine then, if you could actually remove much of the atoms along the side and create an even sharper tip, you would get less of these emission points along the tip. And indeed, if you create a sharp enough tip such that you have only 3 atoms on the very end, then you can get a beam of 3 helium ion beams coming from the tip with some small beamlets around the outside as well. This here is what we call the trimer, or rather these 3 atoms right in the center, this is the trimer. So we're getting 3 beams coming from the end of a source that we can then use to scan across a surface and create an image. So it's worth at this point discussing what the difference is between this type of source and the more common sources that you might experience in the field, being that from the SEM and perhaps a FIB-SEM. So let's start with an SEM. Typically what you would have is a very sharp tungsten tip, as we discussed. You apply a high voltage to this and electrons will stream off of the end form of that very sharp tungsten tip. The shape at the end might be on the order of 20 to 100 nanometers in size. So you get a spot of emission radiating out from this virtual source here. You then demagnify that beam, and the final beam size you can get typically might be on the order of, say, 2 to 5 nanometers, somewhere around there. Very, very small beam size. For a liquid metal ion source, such as an gallium fib, we still have the tungsten tip, but above that we now have a reservoir of gallium, which we heat up and allow the gallium to flow along the tip. At the very end, the liquid gallium forms a pendant droplet, which we call a Taylor cone. That little droplet has a size of, say, around 10 to 50 nanometers, so a bit smaller than the field emission source. But the demagnification ratio is not quite as much with gallium, and so we end up with a final beam size of, say, around 10 nanometers on the high end. So still very, very good precision for a very heavy ion, but not particularly good for imaging because it is very damaging, but very, very good for fabrication. The gas field ion source is different to both of these. We're still using that tungsten tip, but now we've sharpened it down such that we have atoms on the end. We cool it to about 80 Kelvin through a cold finger attached to solid nitrogen. And then we surround this atomically sharp tungsten tip with helium gas. And as we said, when the atoms approach the end, they are ionized within these ionization disks, and then we get beams coming from those atoms. So now our probe size, or our virtual probe size, is on the order of the atomic separation of these tungsten atoms. So now we're looking at a virtual probe size of about 0.25 nanometers, significantly smaller than either the field emission source or the gallium liquid metal ion source. However, our demagnification here is almost 1-to-1. So our final beam size is about the same size as the probe size. And it's a lower limit of about 0.3 nanometers for the helium ion. The downside to having a 1-to-1 demagnification is, of course, this is then incredibly sensitive to vibration. If this tip wiggles a little bit, the spot will wiggle a little bit. So it's very, very sensitive to vibration, but it is also incredibly well collimated because of this. But how do we get that very, very sharp tip? We start with a single crystal tungsten tip that has been fib milled to a point. But as we've discussed, even though that's incredibly sharp, it still has a round end form. So our emission pattern would look something like this. Zeiss then apply a proprietary technique to form the source, whereby we extrude these atoms down into a pyramid. And this is an automated process within the software. So when we need to form a new source, we tell the software we need one, and it creates this pyramid structure. That's still not enough though. It creates a pyramid, but it doesn't give us these 3 atoms on the end. That final step we have to do manually by field evaporating the remaining atoms around the trimer. So we might end up getting something like this after a source form, where we see we have a triangular pyramid structure coming from the field emission pattern, but it's not a trimer. So what we have to do is we turn up a particular voltage and we field evaporate the outermost atoms in the source. And we can watch this live inside the instrument, and it looks something like this. So one by one, these atoms, we can evaporate away from the tip until we end up with just 3 on the end. And this now forms our source. But we don't point all 3 beams down the system. We only want one of these to go down the column. So you can see this is a little bit misaligned in the image. And it's somewhat represented by this schematic here, where we have our 3 beams coming down, and they're not passing through our little beam defining aperture that's just below the source. So what we do is we tilt this tip to point only one of these beamlets down. So we tilt it like that and align a single atomic beam down our column. Everything else then is very similar to an SEM. So we have electrostatic lens system and optical column here that takes that beam, passes it down through and onto the sample. When the beam interacts with the sample, we can then raster it left and right and up and down with the scanning coils just above the objective lens. And when we do that, we generate electrons coming off of the surface. So the helium ions are stimulating secondary electron emission from the surface, and we then collect those secondary electrons within a fairly standard Everhart-Thornley secondary electron detector. We raster that beam down and we count the electrons. So what we get, just like in an SEM, is a rastered secondary electron image that would look something like this on the right. So that's the basic process for the helium ion microscope, and you'll see that it is really not significantly different to the SEM. The big difference is in the way that we generate the source. But why are we using an ion beam anyway? And this is an important question. So the smallest spot that we can achieve is going to be limited by the wavelength of our probe due to diffraction. So helium ions are over 7,000 times heavier than electrons. So they have a wavelength that is much less than that of an electron at the same kinetic energy. So you can see here a helium ion at 30 keV has a wavelength less than 0.1 picometers. So by using ions as our probe now, diffraction effectively becomes negligible. So the fact that we can almost ignore diffraction and we have a smaller virtual probe size means we can achieve a much sharper beam and get better resolution. So if we were to look at the contributions to probe size in this chart here, we have brightness or beam current, diffraction due to wavelength, chromatic aberration due to energy spread, and spherical aberrations due to the lenses. Combining all of those together, we get this black curve. And you can see it has a minimum point down here for the helium ion microscope of about 0.3 nanometers. Now, very crudely, if we were to say that the brightness, chromatic, and spherical aberrations are going to be similar for an electron column, and we only change diffraction, we might see something like this, where diffraction now pushes the limit up further, and we get an SEM resolution of, say, 1 to 3 nanometers. This is a crude comparison, but it kind of gets the message across, that this is what we're talking about, the difference between the helium ion and the SEM. So the benefits then are in resolution. So if we look at this comparison by the researchers in the citation below, we can see we have a field emission SEM image at the top and helium ion images below of HeLa cells. And if we go straight down to the highest magnification, 700 nanometer field of view, the SEM, you can see a lot of detail. This is a stunning image, but with the helium ion, you can see more. It is a sharper image with better surface detail and nano-textured detail in this image. Depth of field is another big difference between the helium ion and SEM. And this is due to that incredibly collimated beam. So these are a light absorbing nanopillar array, and the SEM image you can see goes out of focus quite quickly. The helium ion stays in focus for longer. It has greater depth of field. And finally, surface sensitivity. These are aluminium pads with some surface contamination on the top. In the SEM, you can see this surface contamination, these little black spots, but not quite as clearly as you can with the helium ion microscope. So where does this come from in particular? We've talked about depth of field and resolution, but where does surface sensitivity come from? And this is due to the ion surface interaction. So if you think about an electron beam, we have a probe coming in and the electrons will hit the surface, create secondary electron emission from that point, but then they'll continue to travel into the sample. And when they do this, they scatter around and they generate Se2 secondary electrons, and they also generate backscatter electrons. So this bulb of interaction volume here is where you get your signal from. So it's a combination of Se1 from the surface and Se2 from more bulk information. So it is a combination of the surface and the bulk information in SEM. And that would give you an image something like this. If we look at the ion surface interaction for the helium ion microscope, what we get is a beam that comes in, immediately generates secondary electron emission from the surface, but the moment that this happens, it is now neutralized. It grabs an electron as quickly as it can, and it travels the rest of the way as a neutral species. It's also only generating secondary electrons from very shallow, or rather that the electrons that can escape are only from a very shallow area. It might generate secondary electrons down here, but they will be so low in energy that they cannot simply escape out of here. Now you'll notice as well that the information depth for the helium ion here, if we're saying is around 10 nanometers, to achieve that with an SEM, you need to have a low accelerating voltage, about 500 EV. So this now becomes far more surface sensitive. We're only really getting information from the topmost layers. So it's only SE1 and is only surface information. And that's what gives us this enhanced surface contrast. So it makes it particularly good for imaging ultra-thin films like graphene and carbon membranes. So these researchers were creating ultra-thin carbon membranes from different precursors. And the one I want to draw your attention to is the one in D, which has a thickness of 0.6 nanometers. And we can still clearly see this ultra-thin membrane across the copper TEM grid. And we can see all the beautiful folds and ripples in that film as well. In some of the thicker ones, we can see where it is laid on top of itself and created multi-layered areas. And we get that different level of contrast coming out as well. Now, there's another aspect of this ion surface interaction that makes the helium ion microscope quite useful. And you'll notice with the electron beam that we're generating a positive charge at the surface because of this secondary electron emission. So we're removing electrons and creating a positive charge at the surface. But an electron travels through and is always negative. An electron is negative after all. So there's a subsurface negative charge. Now, to deal with this charge, you can imagine that if you have a positive charge at the surface, it would affect an electron beam coming down and electrons trying to escape. So to deal with this in SEM, typically the practice is to coat the sample with something like gold or carbon to soak up that charge and dissipate it away. An alternative approach would be to try to balance the surface and subsurface charge through low voltage SEM as well. But that's quite a tricky process and it's not going to always work. In the case of the helium ion, you'll notice that our charge here is always positive. This is because we're hitting it with a positive beam, we're emitting electrons, so any charge that comes from this arrives at the surface is going to be positive, and subsurface, it is neutral. So our charge is always at the surface and our charge is always positive. This means that in the instrument, we can use an electron flood gun to image insulators without that gold coating. So we do that by scanning the beam across and we generate that positive charge, but now we introduce into the experiment an electron flood gun. And what we do is we point that electron flood gun at the area that we are scanning with the helium beam, and we give the surface some negative charge. And through some instrument parameters, we balance the negative charge with the positive charge to neutralize the surface and allow us to image insulators without that coating. So here's an example of filter paper on carbon tape. An interesting thing with the helium ion microscope, when surfaces charge up, they go black, because as you can imagine, the surface is positively charged here, so electrons cannot escape, so there's no signal. So when we see a black surface, it quite often means that the surface is charged up. And this is the carbon tape here that is still conductive. But now we turn the flood gun on, and all of a sudden we can see all of that information again. So the last little part of the ion surface interaction I want to introduce to you is that of ion dosing and nanofabrication that we'll talk about towards the end. And this is the fact that we're using an ion beam after all. It is a high energy ion beam, and the momentum of those ions we can use to create structures. So there's some conditions here, sort of default ideas about the spot size, energy range, and current that we can achieve. And what we can do is, into gold in this particular case, is we can create patterns and structures with very high fidelity. So these are 100 nanometer square apertures in gold, created into an array just for a little bit of fun within the software. And these are 7 nanometer gold lines that were demonstrated on the instrument when it was installed. So this is gold on glass with a 7 nanometer gap size cut into the gold with the helium beam. On the instruments that also have the gallium fib column, you can use the gallium to create a very, very large structure. Then use the neon within the gas-filled ion source, which I haven't mentioned yet, but we can have neon and helium through this source. You can use the neon to do some finer structuring, and then finally use the helium to do the finest details. And then we can create arrays of those structures as well. So you can create very many devices for testing. Okay, so let's combine all of this together. Let's go through some examples and a little bit of a slideshow of the research that our instrument is seeing and what our users are interested in. And then towards the end, we'll do a couple of case studies on the fabrication side of things. And then we'll talk about the future of the technique. So to start us off, we're going to go through some biological structures. So what we have here are some fetal utricle cells. So these are inner ear structures. So this is the bottom row here. These are inner ear structures. And within the inner ear, we have these very tiny hair-like cells. And this is what gives us our sense of motion. Now, the thing is that these are easily damaged and they don't regenerate. So these researchers have been attempting to recreate structures similar to this using stem cells. So the top row is this organoid that they created, and they were able to show very similar hair-like cells on their stem cell grown structure. So this is a potential pathway to regenerate the ear sensitivity. So this was imaged with the helium ion microscope at the University of Melbourne. And of course, this is without a coating, with very high resolution and good surface sensitivity to see all of this very rich detail. We have researchers that are very interested in the way that cells stick to polymers. You can imagine that you might want to create a biomedical device where you either do or do not want the cells to stick to that surface. So these researchers are interested in how they can engineer the polymer surface to change the way cells stick to them. So they're using the microscope and the ability to see these structures without the coating and to see surface details with this microscope rather than the SEM. Some more cells, these are red blood cells. And these researchers are actually interested in the surface texture of red blood cells because this is an avenue for the malaria parasite to infect cells. So they're not so much interested in the whole cell or the cell life and death, but rather the surface texture of these cells. So if we zoom in on this stressed cell on the right-hand side, we can start to pull out this very lovely surface nanotexture on the cell. We can zoom in a little bit more and start to see this texture and this pitting on this red blood cell. So they're interested in how this texture changes with infection. Some drug-resistant bacterial infections. So these are typically hospital-acquired infections now. These are Bormanni cells, bacterial cells. So these are an almost spherical but rod-shaped bacterial cell. And what these researchers are doing, and particularly the group from Neil O'Brien Simpson, we're looking at cell life and death here. So they're creating different treatments and different surfaces to see whether these bacterial cells survive on these surfaces. So on the left, we have healthy bacterial cells, and on the right, we have very, very unhealthy bacterial cells. So with different treatment regimes, we're comparing the good cells versus the bad cells and counting how many of these bad cells are there for each treatment to see which one is the most effective to treat these drug-resistant bacterial infections. Another example of the same line of research, but now with something that you might have heard of, this is Staph aureus, or in particular drug-resistant Staph aureus, or MRSA. So we have the healthy Staph aureus cells on the left and the unhealthy Staph aureus cells on the right with different drug treatments. So it's the same approach again. We're looking at cell life and death and counting how many of these different dead cells we see for a given treatment. But with this particular line of research as well, what we did very early in the year was to take some of these cells and cut them open. So here we have some top-down views of the Staph aureus cells, and you can see these little rectangles that have been drawn onto the images here. So this is where we've taken the neon beam and now created a pit right over the top of one of these cells. So we were looking to see whether or not we could identify anything happening at the surface. So the interface between the cell and the polymer surface here. Now in this particular part, we didn't really see much. This was very much a first attempt at this research, but you can see that this is the power of this particular source, that we can create very, very fine structures for milling surfaces away, and in particular milling very soft materials such as bacterial cells. So this is very much ongoing research. We do a lot of work with biomedical devices. This instrument is in the Department of Biomedical Engineering after all. So these are electrode pad surfaces from the stentrode. So this is a stent-shaped multi-array electrode that can go up into the vascular system in the brain to stimulate and to read electrical signals within the brain. These are what some of the pads look like. So they're very, very small, thin metallic pads with a conductive surface on the top. And you can imagine that the surface area of those pads is very important for the electrical contact. So these researchers are interested in what's happening at the interface between these deposited layers and what is happening at the surface before and after usage. So we zoom right in on these and we look at the surface texture of these contact pads and monitor how these change with usage and under different conditions. This is now a bit of a collaboration between multiple Ant Victoria hubs. So we're looking at carbon fibers here, and we're looking at coated carbon fibers to change their surface properties. So on the left, we have pristine carbon fibers imaged within the microscope. And on the right, we now have plasma polymer coated carbon fibers. The interesting part of this work is that we're actually exploiting something that otherwise we would try to get rid of. And that is we're exploiting charge to create contrast. Because this center core of the fiber is of course conductive, but the polymer coating is somewhat insulating. So we're balancing the electron flood gun to give us this very clear contrast where the coating is and is not on the carbon fiber. The researchers particularly like the helium ion microscope in this case, because all of the SEM work that they've done in the past, they've not been able to actually clearly see with this level of contrast the coating on their fibers. So the helium ion is giving them a whole new look at their carbon fiber coatings. And if we zoom right in on these, we can see the thickness of the coating, the carbon fiber here, and we can see surface texture on the plasma polymer coating there as well. These are building materials now, fire retardant building materials, so fibers to create building cladding. And there's been a lot of stories in the media recently about cladding on buildings catching fire and spreading the fire up the building. So these researchers are interested in creating fire retardant nanocomposite building materials. On the left, they have the fibers that make up the bulk of the building material and the structural strength of that material. And on the right, these are the coated fibers. So these little nodules and balls all over the fibers are the fire retardant coating. And here we are again using the resolution and the surface sensitivity of the helium ion microscope to get these images. This was proving a challenge for the researchers to do with SEM because they needed the coating, but the coating was not coating very well onto these fibers, so they were still getting lots of charging. And TEM gives them stunning images, but TEM was requiring quite a lot of sample prep. So the helium ion was a nice balance between the SEM and the TEM, giving them the resolution that they needed with minimal preparation of their samples. Some ultra shallow nanostructured polymers now. So this is using the nanofraser technique at MCN within Ant Victoria. So this is thermal scanning probe lithography, basically taking an AFM tip, heating it up to 1,000 degrees, and that sublimates a polymer and creates these patterns here. So the images on the side here are from the helium ion microscope. So this is imaging directly onto the polymer. And these patterns are about 25 nanometers deep, so incredibly shallow. And we can actually see the individual pixels. So everywhere that this tip has tapped to sublimate a small amount of that polymer, we can see each of those little taps. And we zoom in, and they were very interested in the fact that there was this artifact on one side of the scan line for the nanophaser. So they were interested in what was going on right at the end of the scan line here. And now we can't have a presentation on the helium ion microscope without talking about some graphene. So this is laser scribed graphene oxide from my time at Newcastle University. So this is using an argon laser to generate a tremendous amount of heat in a deposited graphene oxide layer and create reduced graphene oxide. So each one of these lines is a pulse of the laser. And this is the point at which the laser strikes the graphene, and then it is rastered across here. And this is an explosion outwards of accordion-like reduced graphene oxide from the graphene oxide layer. Now, again, interestingly, this is all on a polymer substrate, and this area is not particularly conductive, but this is very conductive. So again, by balancing the flood gun, we can make everything come out with beautiful contrast. If we zoom in on the areas where the graphene oxide has expanded outwards into this few layer reduced graphene oxide, we can start to see all of these different layers and understand how this is exploded outwards, like I said, like an accordion. But the interesting part was actually on the surface, where we could see all of these tiny little nanoparticles all over the graphene surface. Okay, so now getting into some of the more ANTH-like case studies. So here we're looking at some diamond, superconducting diamond in particular. And these researchers are making ultra-thin diamond, superconducting diamond films through the deposition of quite a thick layer, 300 nanometers, and then etching down to create ultra-thin layers of about 50 to 120 nanometers on silicon nitride. The researchers, we were then taking this diamond and creating an array where we create patches of different ion dose, either using the helium or the neon ion beam to create defects up to these different ion doses. So we have a range from 10 to the 11 up to 10 to the 16 ions per square centimeter. And we're penetrating about 100 to 30 nanometers, depending on whether we're using the helium or the neon beam. And from this, from photoluminescence, we can see that we create photon emitters. So 10 to the 11 and 10 to the 12, we don't see much photoluminescence. But once we hit the 10 to the 13 dose, we start to see some photoluminescence under laser irradiation. And at 10 to the 16, we of course see the most. And depending on whether or not we use the helium or the neon beam, we can actually create emissions of different wavelengths from this diamond. So the helium beam creates an emission of about 560 nanometers with a 532 excitation. And the neon is creating a slightly shorter wavelength of 548. And we believe this is due to the sizes of the defects within the diamond. The ultimate goal here is to be able to create single photon emitters from very, very small areas on a diamond substrate. Okay, so now we're getting into the last case study just before we talk about the future of the technique. And we're now talking about some plasmonics. So some researchers from the School of Physics are creating apertures where they can trap nanoparticles. So these are what they call double nanohole apertures, and they have a gap here of about 30 nanometers. If they illuminate this double nanohole with a laser, they can create an incredibly strong electric field in the center that is enough to trap a nanoparticle in that spot. And they're using these traps to study particle motion. So on the right, we've got a short video here, and what I've got outlined is roughly where the double nanohole aperture is in the video. If I click play, this is the little nanoparticle. They turn the laser light on and it gets trapped into this double nanohole. So if I scoot over this way, you can see the particle trapped, and then they eventually turn the laser light off, and this nanoparticle will let go and start wandering around in the fluid again. This is all inside of a water chamber. So the laser was turned off and the nanoparticle can wander away. Now you can imagine that this is quite a human design. This is creating a gap with a pair of circles. This sort of makes somewhat an intuitive sense. So following on from that work, Newton decided to take that work and decide to let the computer design what the nanohole should look like. So they took the original design and they said, we want this gap to be the same. We want this to stay 30 nanometers, but you can change all of this. And they let an algorithm optimize the electric field enhancement by changing that shape. And the final design that the algorithm came up with was this squiggly one. And you'll see that the enhancement goes from a maximum of 11.5 here up to 24. So more than double the enhancement. And with a ring structure around there to capture the light as well, they can go from this level of trap potential up to or down to this level of trap potential. So much greater enhancement by letting the algorithm decide what the shape should be. So this original double nanohole was created with a gallium fib. And so this was the new design that they needed to achieve. And this was the result that they got from the gallium fib, attempting this with the new design. Now, of course, this doesn't really look significantly different to the double nanohole, and it's lost much of the fidelity of this design. So the challenge was now to create this structure using the helium ion microscope. So here is the result that we got from our instrument using the neon beam to create the ring and the helium gas-filled ion source to create the internal structure. And the comparison is quite clear, really, the difference between the two techniques. If we zoom in on that structure, compare the design to the result, you can see the fidelity with which we can reproduce structures, with realistically actually quite a modest gap size still of 30 nanometers. Now that's not to say that a modern gallium fib instrument cannot achieve this, because there are some new instruments that are very, very precise now, but this is just the comparison that we've seen in our research. The other advantage to using the gas-filled ion source versus a liquid metal ion source is in the shape of the beam. So here, the neon beam and the helium beam is creating vertical sidewalls, whereas the gallium fib has quite a large Gaussian profile, and so we end up with these rounded edges on the devices that are created. Interestingly, from this work and from much earlier work, the limitation here is not necessarily due to the probe size, but actually due to the grain size of gold. So some researchers a number of years ago showed this with gold transmission apertures here. And so this is a gap of 8 nanometers. And their comment was that the fabrication of these antennae is not really limited by the helium ion lithography probe size, but is now limited by the grain size of the gold itself. So shifting to something like single crystal gold deposition might be a way to achieve a much finer structure again. Okay, so we're getting towards the end here, but the last thing I wanted to talk about with this webinar is a question that I get asked a lot when I'm introducing people to this system, and that is microanalysis possible with the helium ion microscope? Because a lot of people that come to me, of course, have come from SEM. The answer is yes, but it's not the way people think of immediately. It's not EDX. There is no EDX-like capability with the helium ion microscope like there is in SEM. So why is that? That doesn't seem to make sense, does it? So let's think about what we actually need for characteristic X-ray emission. We need an ionizing particle, and we've got that. We need enough energy. We've definitely got that. We need core level electron ionization, and we don't have that, at least not in significant enough amounts to be counted. So why is that? Well, that's because we don't have a velocity match, which is a very good rule of thumb for identifying whether or not you're going to get core level ionization. So we have to remember that even though we're dealing with a 30 kV helium ion beam, it's much heavier. So its velocity is far lower than the electron beam. So in other words, the very fast electrons in the core of an atom, we cannot excite because we're going too slow. So it's interesting that we have very, very good ion-induced secondary electron yield, but we don't get core electron yield. So we're much better at getting outer shell electrons. So what can it do then? So the technique that's being developed is one of mass spectrometry, HIMSIMS, helium ion microscopy, secondary ion mass spectrometry. So there is a small and appreciable sputter yield from neon and helium. And of course, we've seen that already because we're fabricating structures by removing atoms. And a small percentage of this is actually ionized. So researchers within Lion Nanosystems have created a system that is a through-hole mass spectrometer. So the beam passes through an initial lens, and then ionized ions come from the sample surface and are passed into some transfer optics and then into a magnetic sector analyzer. So these ionized atoms that are coming from the surface, they get sniffed up into here and mass analyzed. On the instrument Newcastle University in the UK, this is what the system looks like. So this is the microscope and this is the sector analyzer dangling off to the side. So what can it do then? You would think that, oh, excellent, we can get 0.5 nanometer resolution SIMS. That's amazing. But it's always a bit of a trade-off. So we can't get that sort of resolution. However, we can get a lot better than the best dynamic SIMS systems out there. So once you account for the primary beam size, the secondary optics, and the way that your beam interacts with the sample, you can get something around 10 to 15 nanometers as a lower limit for the spatial resolution for SIMS on a helium ion microscope. So this is a vast improvement over the sort of 50 to 100 nanometer resolution from something like a nano SIMS. So we're talking about this red spot versus these green spots here. So it's still better, but it's just not as high as perhaps you might have thought. So this works quite well. So this is a BAM standard of gas, AlGas, so aluminium and gallium. And if we just scoot across to here, this is the aluminium intensity scanning across this layered structure here. And you can see that the system can identify down to a 3.5 nanometer isolated line of aluminium. So this is looking at these ideal layered structures, and we can identify very, very small structures. So it's good then for looking at things like nanoparticles and nanowires. These are silver nanoparticles and nanowires investigated for cytotoxicity within the lung air liquid barrier. So these are the nanoparticles here, so 20 nanometer, 200 nanometer, and these are the nanowires. And this is the SIMS signal from silver on a helium ion microscope with the SIMS attachment, and you can see the signal being detected. So you can identify that these nanowires are indeed silver. Now, this image you could probably achieve with a very good EDX system. This one you probably could as well, might be a bit of a challenge. This one within EDX, I'm not so sure, because you have to remember these are 50 nanometers wide, but they're also therefore only 50 nanometers deep. So getting that kind of very shallow signal from an EDX might be a challenge. The only other technique that I would think of that would do that readily would be something like a scanning Auger microscope. So this is very, very interesting being able to see incredibly small nanoparticles on a surface with minimal interaction from the substrate beneath. Some of my own research now, far less impressive, but these are indium phosphide or metallic indium nanoparticles on indium phosphide. So if you etch away indium phosphide, remove the oxide and start to preferentially etch the phosphor, you end up with indium enrichment at the surface. If you continue to etch these with a gas cluster ion source or an argon ion beam, you create this incredibly beautiful nanostructured surface on the indium phosphide. So these are all helium ion microscope images from Newcastle. And we wanted to demonstrate that these are metallic indium. So on the SIMS instrument, we had a look at those. And my colleague, Billy Murdoch, did this HIMSIMS mapping of the indium peak here. And we can see there's some indium signal enrichment coming from the tips, but it's not necessarily clear that that is because there is enrichment there. Maybe just there is better ion emission coming from those tips. We've since demonstrated quite clearly with scanning Auger microscopy that it is metallic, but this was a first attempt at using our HIMSIMS to actually image a metallic species on that surface on the nanoscale. Okay, I think that just about wraps everything up. So once again, this is what I want you to remember about the helium ion microscope. The gas-filled ion source gives us a resolution. The electron flood gun allows us to image insulators without a coating, and the ion surface interaction gives us our surface sensitivity and enables ion dosing and nanofabrication. So the take-home message is it's a high-resolution surface scanning charged particle microscope. It's similar to the SEM, but with higher resolution, greater depth of field, and better surface sensitivity, and we can image insulators without coating. Ions have greater mass than electrons, so shorter wavelengths, and this is where the resolution comes from. And so it's very, very well suited to looking at soft matter and biological structures, thin carbon films, and anything that would otherwise require a coating to image it. And we can, of course, use it for materials engineering and nanofabrication. So thank you very much for watching with me. We will have a look at the chat now and see if there's any questions that we can answer quickly in the short amount of time that we've got in this session. If you'd like to learn more, please do visit our website here. You're welcome to email me as well and ask me any questions, particularly researchers from Melbourne, Victoria, or Australia. And if you'd like to find out about access to the instrument, please do not hesitate to ask me. Visit our website and have a look at what else the MCFP has to offer you, and get in contact if you have any questions. So we'll just have a quick look at the chat and see if there's any questions. So if you have any questions, feel free to put them in the chat. I'll hang around for another 5 or so minutes until the end of our session. And otherwise, do remember that this is being recorded, so I can share this link with anyone that's registered for future viewing. Okay, so we have a question about preparing a TEM sample. Good question, and that is one that does get asked of us as well. So on our instrument, no, is the simple question there. And you followed it up with exactly the reason why. There are no nanomanipulators on our system, so we cannot do the lift out aspect of TEM preparation. You could conceivably do a lot of the milling and potentially cut the section or find the section that you want, but you would still need to go to a system like a FIBSEM that has a gallium column to do the final lift out. And therefore, you might as well do all of that in the one system, because you would lose any of the advantage that you've gained with using the neon beam, for example, by having to do the lift out with a gallium. There are systems, as I understand it, that do have nanomanipulators on them. So it is a future possibility, but on our instrument, unfortunately not. Okay, so we've got another question about graphene. With a resolution of 0.3 nanometers, can you see a single sheet of graphene if you are not looking at the edges? So we can see the interaction. I guess the key thing there is we need some amount of contrast. So we can see on single layer graphene, or at least what people have told me is single layer graphene, we can see folds and creases and tears. And that's what tells us we're seeing the graphene layer. If you imagine that we had an absolutely perfect graphene layer with nothing beneath it, then we're not going to see the graphene structure or something like that. We would just see kind of a gray image. So there needs to be something beneath it or on top of it to tell us that that's what we are actually seeing. Typically, of course, for single layer graphene, you're going to have that suspended across something of an aperture, like a TEM grid, and we can see the grids beneath the graphene, which is an interesting effect because what we're actually doing there is the helium ion is penetrating through and is generating secondary electrons from both the top and the bottom surface of the graphene. And it is potentially generating secondary electrons on the grid as well. And they are then traveling backwards through the graphene and creating this see-through effect. So we can see the structures that are beneath the graphene as well. And that's, again, another way that we can sort of tell that that's what we're looking at. But if you wanted to be able to say, identify the difference between 3, 2, and 1 layered graphene, I think that would be quite a challenge based on contrast. And I think that there are better techniques suited to that, such as AFM. Okay, so we've got vacuum emissions. If you're putting hydrated biosamples into your HV, would you see any changes in the surface due to the vacuum? Okay, so this is a sample prep question, really. And what I guess I would say to that is anything that you believe you would need to do or that you have to do for SEM, you have to do for the helium ion microscope as well. So we cannot see, or we cannot look at hydrated biosamples in the helium ion microscope. So anything that was biological throughout this presentation would have been appropriately dried beforehand. So the red blood cells, for example, went through quite an extensive dehydration process to maintain their structure, but to dry them out. So yes, if there was something that was hydrated, you would absolutely see a change happening inside the vacuum. So cells would burst, tissues would melt and shrink and all that sort of thing. Next question, does the mass spec aspect only work on flat surfaces? I would expect not. It should work on rougher surfaces. I guess there would be an aspect of that that would limit it. So an incredibly rough surface, you would start to have to deal with kind of the capture of the ions coming from the surface into the analyzer. Having said that, I'm certainly haven't had a lot of experience with that aspect of the instrument. We don't have that capability in Australia. But that's what I would believe is that if you had an incredibly rough surface, you would still need to try to capture those ions. And additionally, the way that the beam would be scanning across the surface, you would potentially be creating shadows where you're not generating ions as well. So from those spots, you would see less signal, which could be misinterpreted as low ion signal, but it might actually just be that the yield from that spot is quite low. So I don't believe that it would only work on flat surfaces, but a flat surface would be preferable, I would expect, much like it would be the case for a TOF SIMS instrument as well. I did not discuss helium ion implantation. No, I didn't. And helium build-up when milling. Any points? So yes, this is a known artifact, well not artifact, a known effect within the helium ion microscope community, and is particularly well demonstrated with silicon. Basically, if you image silicon on a small spot, you can penetrate the silicon and implant helium beneath the layer and actually create a bubble of helium gas underneath the silicon. And what ends up happening is you create a bubble that expands the surface upwards, and you start to get some very, very nasty looking surfaces. And if you're trying to mill into silicon, for example, you would get a very defective looking structure. My only comments would be that we've generally avoided doing work on layers on silicon for that reason. But what I have found is that there's ways you can get around it a little bit, and that is thinking about the penetration depth of the helium ion beam. So if you have, for example, a 100 nanometer gold layer on silicon, if you use a beam energy that's a bit lower than the typical, so say 20 to 25 keV, then you reduce your penetration depth a little bit, and you can keep the helium beam inside the gold effectively. So you're removing parts of the gold where you would be depositing the helium into anyway, and you can get around that. So that's effectively what we do when we've been making those gold plasmonic devices. We actually use a lower beam energy than we would for imaging to help with that aspect. Access to this recording, absolutely. I'll be sharing a link with everyone through Eventbrite. So you should get an automated email with this link once it's been processed. And it's going to be through Australia's RNet cloud service. So it'll be a cloud recording that you'll be able to view at any point. Is milling done in tilted angle in helium ion or like in FibSem? Okay, so this, I guess, depends on the system. So if we're talking about helium and neon milling, then no, we're doing that normal to the surface. So you can, for example, if you're doing the neon milling, so you're removing as much as you can, you're doing that top down, and you can image with the neon beam. It's not great, but you can image. You would then switch back to the helium beam to do your imaging, and you can then tilt your imaging to get the different aspect ratios or get the different view of the structure you've created. But it's not like in a FibSem where you tilt so that your gallium beam is normal to the surface while your electron beam is at an angle, because our imaging source and our milling source is the same system. Having said that, you can get the gallium column onto the Orion nanofab as well. And in that case, you would treat it like more like the FibSem, in that you would tilt towards the gallium column to do your gallium milling and image with the helium beam at an angle. But so it's all about experimental design there as to how you want to go about doing it. Okay, so I think that's put us over the 1 hour mark. So thank you very much for everyone that's attended. I hope you got a lot out of this webinar. As I said, we will be sharing this with everyone, so you'll be able to watch it again another time, and for any viewers that weren't able to make the session. So thank you very, very much, and enjoy the rest of the day.